I mean, I thought it was just
I thought say, like, it's just the jacket, like.
I thought it was at the end of
So,
And the
camera's
puzzle
on, by
pattern.
the way, here we
yeah,
go.
like the one actually.
All right, so, quiz tomorrow, we'll take a little quiz tomorrow, okay? I think it's simple. It's really gonna boil down to how you can operate your calculator or not, honestly. Probably the biggest problems will come from that. Here's what we're gonna do. We're gonna take, the little math problems that we've been doing. So we need to be able to do, we need to be able to take the speed of light equation and calculate either wavelength or velocity, wavelength or frequency, speed of light, one way or the other, or probably both. Okay. I give you the equation, but you need to remember the speed of light. That's just the one little number I think, one of the few little things I ask you to memorize. Okay. Besides your polyatomic ions, which is a whole other deal. So we need to given a frequency, you need to be able to find a wavelength. Given a wavelength, you should be able to find a frequency. I give you the equation, make sure you know the speed of light. Okay. Then using frequency, wavelength, and energy, you should be able to relate those things together. Let me click a button here. Yeah, so like right here, you should be able to find the wavelength and the energy, right? In joules, we're not going to deal with the electron volt. Don't worry about that. But again, all these answers here are provided. Okay, so you can practice, practice, practice. All right, and we're also going to take these numbers. Please do not memorize these numbers. I'm going to give you these values of the energies of each of the 7 orbits of Bohr's model, and then ask you to find the change in energy for a transition, the frequency, wavelength of that transition, so on and so forth. Okay, again, basically this, right? These are the 4 visible transitions. I'm going to pick a different transition, but it's the same process, different numbers. You're given the numbers, you're given the equations. I give you Planck's constant. I give you everything you need except speed of light. Okay. So again, like I said, it's basically going to boil down to you being able to operate your calculator. You get the scientific notation entered incorrectly, that sort of thing. That's really all there is to this. All right. Again, there's answers to those. Practice. Please run them through your calculator again, and then we'll have a question about de Broglie's matter waves. I'll give you some object and its mass and velocity, and you tell me what its wavelength is. Pretty simple. It's not going to operate a calculator. So go through tonight and rework all sets of these problems, and just make sure that your calculator gives you the same answer that we have right there. Okay. 5-minute break.
You guys are great. I'll see if there's anything.
Yeah. Just finish that.
All right, I want to know if this notebook check today was
Right thing? Did Sumner say that our quiz was set?
Yes.
Yeah.
Yes.
But he took it
The
off
quiz is
school
today,
issue.
He said the test. I don't
No,
know.
he said the test is getting moved back to next week. But
He said that?
he said notebook check, and they were giving the rest of them.
Yeah. He said the quiz was this week. Test is next week. Notebook check this week.
You legit said quiz today.
Quiz today. Quiz is Tuesday. Today. Today
No.
is Tuesday.
No.
That's not what he told our class. He told your class wrong.
I thought we were finishing 1.5 then quiz.
Well, maybe our class is on different.
Have y'all finished 1.5?
I
Well,
don't
there's
know
1.5. Graphing? Is it graphing?
It's like 1.5, 1.5.2.
I don't think we've done all that.
3.4.
He told us quiz on Tuesday.
And I also,
He's a liar. This is a sham, okay?
I think he moved it back.
but it's also so hard to pay attention in this class. Because so many people are talking over him that I don't understand anything he says.
I promise you, maybe he's spelled it wrong.
I
I
remember-
misunderstand. Okay? If it's wrong, he's on the wrong.
Yes, he did say that.
Quiz on Tuesday.
He said,
Because
when y'all,
in my head, I was like, oh, phew, I don't have to worry about it because I can just chillax on Monday. And then I was like, oh, wait, never mind, I forgot to do it on Monday. It's on Tuesday.
yeah, he was like, don't show up Monday, because I won't be here, you will, and then we have a quiz Tuesday.
And then he gave us the whole thing. The whole week.
But you would think, you make us finish the 1.5.
Well, you would think
Like,
wrong,
quiz,
but yeah.
then like check notebooks, and then
You
or
would
at least
think,
check
but
notebooks.
your thinking is
No,
incorrect.
no. After
Now, you need to learn how to think correct.
Why? Like, how are we supposed to use our notebooks and check it?
It's checking the notebooks right before the test, but you don't have to check it before the quiz, because you're still doing stuff. I would imagine you could learn something from the quiz and write it down and then use it for the test.
I hope, hey, I hope I'm not learning anything in this quiz. That means I don't know the answer.
You can learn something, I don't know.
That sounds like a.
See, I don't.
Just like that, blow my mind.
That doesn't make sense though.
No, I agree with the quiz thing. I'm just like that.
That doesn't make sense.
What doesn't make sense?
Aren't we supposed to finish 1.5?
No.
Then quiz.
Think about this class. We have quizzes before the test, and we still have more information on it. We're gonna have quizzes
Oh,
here
it doesn't
tomorrow.
matter.
We're gonna have
You
quizzes.
said, like, that's when you're like our benchmark. They're like, stop.
Guys, I'm not agreeing with Gabby on
Why
this
not?
one.
What? Why have a quiz? Huh?
Listen,
Why not
listen.
Have you ever attended school before?
No, that's not what I'm saying.
What you're saying is wrong.
Listen, you take the test, right, on everything. The quiz is supposed to prepare us for the test, meaning everything that's on the test should be on the quiz.
No.
Just simplify.
No.
Then that's the class.
This class, bro. No,
That's
no,
just
we
the
need to get
test.
quiz on people. You know, this is not history, man. We got other things to know.
It's also open notes.
I'm aware. I'm just saying.
The quizzes don't have everything. That's the point of
They're
the quiz.
supposed to have majority of things on it though.
It will have the majority.
No, because we still have like a good like 90% of 0.5 to do. So if the majority is to be half, it would be 50% of the 1.5.
We may have 90% of 1.5, but we finish 95% of the chapter.
No, that's not. No. You understanding me, man.
No one understands.
I do.
Why can't y'all just understand how my brain works, you know? Like,
Because
why can't
quizzes
y'all
don't have
just
anything on them.
Exactly. So why would we do like a quiz when we haven't even learned 0.5 yet?
They don't have everything
1.5.
on, so we don't have to know 0.5.
We have such a little inkling left to learn, okay?
No, we don't. We have legit like 5 more presentations left.
You basically have 5 more
And how
references.
do you
Yes,
know this?
it's presentations are
On what basis?
Yeah, have the 5 minutes out. We didn't post them until today we're doing them.
All right, here we go. So, practice, as we were saying, right? So we left off last week. Where did we leave off? Right there. So we had our two, let's just back up a little bit. We had 2 parallel timelines going, right? So we had Thompson and Rutherford, okay? Thompson found the electron, Rutherford found the nucleus, all about the same time. Planck found quantized energy, Einstein found photons, right? Not found them so much as proposed their existence, okay? Mathematically shown that they were such a thing, all right? All right, so those 2 things basically run together with Niels Bohr, correct? He used Thompson's electron, Rutherford's nucleus, Planck's quantized energy, and Einstein's photon to come up with this model. Remember that a model is not a real thing, or it's not the actual thing, okay? It's a model of what we think the actual thing might be. And it worked really great for hydrogen, but not anybody else, right? So, the first thing that we came along with after that might need to be added or adjusted by that model was these matter waves or de Broglie waves, or whichever one you want to call them, right? Was that the electron is better thought of as a wave instead of a particle, and not to get all into because like we've said, the math to that is way past high school, but basically there's 2 sets of there's equations that govern particles, and there's equations that deal with waves, right? And if you apply the wrong equation to the wrong thing, you get the wrong answer, which sounds reasonable, right? So de Broglie basically come along and said you put the wrong equations to the wrong thing. So treat it like a wave instead of a particle, and it might make more sense. Heisenberg come along and decided that we don't really know anything anyway, okay? So that's where my little tennis ball's at, right? So that's where we had our little example of if we somehow, because you gotta remember now, these guys for 20 some odd years, 25 years of physics have been looking for the electron, right? What they want to do with it is be able to give it a set of equations that predict its time and place and motion, just like we do in Newtonian physics, okay? So just like we got a car driving down the highway out here, or the road out here in front of the school, if we know its current location, its speed, we can make a very safe prediction about where it's going to be in 1 second, or 10 seconds, or 10 minutes, or whatever, right? Okay, with a few assumptions that it maintains that speed and maintains a straight line and all that stuff. With a few assumptions, we can make a pretty good prediction, okay? So that's what they wanted to be able to do with these electrons. There's even some deep philosophical stuff about being able to predict the future and things like this that they thought they would be able to do. They could map out electrons and molecules, and in theory, think about this. This gets deep here, so I want you to ponder this for just a second. Like if it were possible to know the speed and position of all of the particles in your that make up you, okay? And then if that were possible to know, if I had a computer that could somehow compute all of that, and then compute where all of your particles will be 5 seconds from now, 5 minutes from now, or 5 years from now, then we could therefore compute the future, where you would be and what you would be doing, and what you would be thinking, and all this other stuff. So that was actual some philosophical ideas they had back then. It's like, we can figure this out, we may get to figure out all kinds of stuff, right? But what they figured out was you can't figure that out. Makes sense, I guess, right? So if you find, it goes back to our little vision experiment of what do you have to do to actually interact with another object, is you've got to have some type of photon radiation interaction, right? Photon's got to bounce off the object and hit you in the eye so your brain interprets there's an object there. Well, the act of actually seeing, quote, seeing something changes it, right, in an unknowable way, so that the only thing we know is that the electron is not right where I thought it was. So what you know is that of all the infinite possible places the electron could be, we know it's not in that one spot, which is not very useful information, because it could be in an infinity minus one other possible places. So we don't know anything, right? So that's what Heisenberg came up with. It's a philosophical argument, and then he also, the interesting thing is when philosophy and science meet together is when you put math equations to it and you actually show mathematically that this is a thing. So he came up with this equation that we're not going to actually do math with. Just you need to kind of understand that the uncertainties in position and velocity are always bigger than the very, very small number of Planck's constant divided by 2pi. But that's a really, really small number. So it doesn't matter for people, right? We had the fun little conversation about whether we're actually sitting where we think we are and all of that stuff. For the most part, yes, okay? But if you get down on the atomic level, the answer is no. You're not where things are not where you think they are. Okay? Now, then, so we got to deal with this in some other kind of way. So we come up with this concept of probability. And Schrodinger's cat going in the box, alive and well, okay? But once it's in the box, is it still alive? The key word is probably, right? We don't have any reason to believe it's not alive, but we can't prove that it's still alive. So it's probably alive, right? In fact, in quantum mechanical terms, and again, this the math behind this gets really, really past high school, but it's both alive and dead until we can figure it out. Because both possibilities are true until proven false. Okay? So, but it's probably alive, okay? So you take that back to atomic theory, and the electron is probably in the atom, okay? Because it doesn't really make sense otherwise, right? And it doesn't really make sense that the cat would still be alive because I just put it in there alive and shut the lid, right? So how could it's probably still alive. Well, the electron is probably in the atom. It's got to be somehow or another. Nothing in nature makes any sense at all. So it's probably there. Well, how probably is it? It's 90%. So 90% probability, okay? And that gives us what we now call an orbital. So I don't know if we mentioned that word last week or not. But Niels Bohr said electrons were in orbit around the nucleus. Same word as an astronomer would use about planets around the sun or moon or the earth. And he's changed the word. He made this word up. It's a twist on the old word orbit. He said now that things are found in orbitals, which are regions of 90% probability. Yep. Yep. Everybody following that so far?
Yes.
All right, so pretty deep stuff, but interesting, I think. All right. Now, what we're about to talk about is going to be confusing at first, okay? And it's not going to make any sense probably today at all right? This is one of those lessons that I wish we had about 3 hours. I really need about 3 hours to get everybody to understand this. Most people, though, who play along with me here, this clicks with you somewhere in the next 3 hours of us talking about it, okay? Most people won't take near that long. Some people it might take 3 hours. I don't know. So I'm saying it might be by Thursday or Friday, okay? I wish we could just sit here and talk about this till a little after lunch, until we figured it out today. That would be perfect, but we don't have that schedule. So we're gonna start talking about this stuff, and then we're gonna have to just stop when the bell rings, okay? And you're probably gonna be thinking, what in the world is this even about, okay? Because I just can't get to the point really today, but we'll try. All right, so anybody ever wrote? Probably not, because nobody ever does anymore. But in the old days, if this were 1950, and you decide you're going to go to across the country like to California, how would you probably go? What would be in 1950? The best way would probably be in 1950, not in a wagon, in 1950. Train. You'd go on a train, okay? So a train. Now, you would have the option to fly, okay? So you would have. You would have the option to drive in 1950, but there was no interstate system, okay? And the roads were kind of iffy, and they weren't real good speed limits, okay? So it would probably take you a good week or so to drive to California, okay? You would have the option of flying if you were super wealthy. You'd have to be, you got to have some money now to fly, but you'd have to be only the super wealthy could afford a plane ticket in 1950, okay? So most people, if you needed to go to California, you'd take a train, all right? There were a lot of passenger trains back in those days. If you went to, say, even Anniston, there would be multiple trains a day. If you went to Birmingham, there would be a lot of trains a day going in all kinds of different directions. So if you bought a ticket to California, you're going to have 4 pieces of information on that ticket. That ticket's going to tell you which train to get on, which car on that train, which row of seats on that car, and which seat in that row. Okay? Similar to an airplane, except an airplane only has one compartment normally to sit in, so you don't get to choose your car, right? But what we're saying is that there's 4 pieces of information on a train ticket. Which train, which car, which row, which seat, okay? The quantum mechanical model of the atom gives us 4 things that we can know about an electron, okay? Number 1 is the same as the Bohr model. Number 1 is we know the energy level, okay? There's numbers for all of this. It will be a day or so before we get to see what these numbers are. But what we're getting to here is that there's an energy level, there's a type of orbital, number 2, there's the orientation of that orbital, number 3, and there's the spin of that electron, number 4. So we can know, according to the quantum mechanical model, the energy of electron, the type of orbital that it's in, basically you can say the way that orbital is pointing, its orientation, and the way the electron is spinning. 4 things we can know. So what we're going to learn today is how we can diagram that. Okay? So we're going to draw these diagrams. They're called orbital diagrams. And it's going to look like a bunch of gibberish as we first start. Okay? It's going to just look like a bunch of random lines and arrows and stuff. You're going to think, what does this mean? Okay? Let me get to about a dozen elements or so and it'll start to click. Okay? Problem is I can't get through a dozen elements for bell rings today, so you're going to have to just pause. All right. Really? All of that. All right. Yep.
All of it? Yes.
Hey, let me,
Hey, my notes are for me.
this
You can't read it, it's your phone.
is one of those.
I got it. Yes, sir.
All right. Before we get too deep into this, make sure everybody's got a periodic table in front of them, okay? If you need one, there's some on the front table. Just don't take my last one, because I need to go make some more copies, okay? The periodic table is going to be very, very handy right here in 2 minutes. Okay.
I think it's got it. I think it's-
All right, so here's what we're talking about when we say that, electrons have a certain energy level. Our choices are 1, 2, 3, 4, 5, 6, or 7, right? We learned that with the Bohr model. So then the next thing is we said we got to know what type of orbital we are in. Well, there are 4 types, okay? And they have, seems like to me, some random letters, just their names. There's S, P, D, and F, okay? So these are S, this is an S orbital. These are P orbitals, the yellow ones here. The blue and purples are the D orbitals, and the greenish colored ones are the F orbitals. Okay? You do not have to remember these shapes or anything like. You don't have to draw any of this. Okay? So don't panic. All right. You don't have to remember the individual names. That's for college class someday. Do all that. All right. What you do need to remember is that S, P, D, and F, and it goes 1, 3, 5, 7. So there's 1 S orbital. There are 3 P's, 5 D's, and 7 F's. That's what we did there. So it goes S, P, D, F, 1, 3, 5, 7. So now we're going to all say that together. We'll never forget it. You ready? SPDF 1357. All right, one more time. SPDF 1357. Okay. All right, now that's important. Okay. We will see here in just a little bit. All right. What we're going to draw here today are orbital diagrams. It's a way that we determine the electron configuration. So what does it mean to configure something? In other words, we arrange it, right? So how are these electrons arranged inside this atom? Okay, we're trying to figure that out, and then we want to diagram it so that we can keep up with it, but also we're going to, in the future, down the road, for other units, we're going to need to analyze the arrangement of these electrons, because that's going to help us figure out things like physical and chemical properties of certain elements. Okay? All right. 3 principles or rules to know. These won't make any sense until we actually start drawing them out. We're going to talk about them first. Okay. The Aufbau principle, that means to build up. Aufbau is a German word. This is not named after a person, so there was not a Dr. Aufbau. This is to build up. The Aufbau principle tells the order in which orbitals are filled. Simplest way to explain this, I think, is has anybody ever played Connect 4? I've seen some know what I'm talking about at least, right? When you drop the little chips in, where do they go? To the bottom, right? Okay, they go to the ground. We call that the ground state. But when that bottom row gets filled up, where's the next one go? To the second row, which is kind of like the new ground, right? It's like a new bottom, okay? Electrons do the same thing. They're going to go as low as they can get. But when those low energy levels get full, then the next ones have to stack on top at a higher energy level, higher and higher and higher. Follow that? That's what the Aufbau principle basically means, okay? The Pauli exclusion principle says that you can only put 2 electrons in an orbital together. And to do that, they have to be spinning in opposite directions. We're going to explain this spinning thing in just a second, okay? But the main thing to remember about the Pauli exclusion principle is each orbital can have 1 or 2 electrons, never more than 2. It can have only 1, but it could have 2. But if it's got 2, they have to be spinning in opposite directions, okay? We'll have to get to element number 6 before we explain Hund's rule, but we'll go ahead and read it right here. Equals energy orbitals are filled before electrons are paired. Okay, we'll see what that means in a minute. Let's talk about spin right quick before we start drawing these on the board. How much time do I have? 20 minutes? Okay, good. Good. All right. If you've got 2 pencils or something you want to do this along with and prove it or not, you can, later on you can do this and prove it to yourself, okay? But I'm going to take these 2 markers and I'm looking down at the top of them. And I'll rotate both of them clockwise, okay? So they're rotating clockwise. Here I go, okay? Looking at them clockwise. And I'm going to take the one in my right hand and I'm going to keep spinning it the same way, but I'm going to flip it over, okay? Now when I look at it, it's rotating counterclockwise, okay? In other words, it's now spinning the opposite direction of the other one. And all I did was flip it over, okay? It's still spinning the same way, I just flipped it upside down, right? Okay, so electrons spin, they rotate on an axis like planets do, okay? They spin like so, all right? That generates a magnetic field. Okay. Electrons, being both negative things, don't like each other. There's a natural repulsion that takes place. The only way they can stay in a region together, in space, an orbital together, is to be, one has to be flipped over so that their magnetic fields are opposite. Because the spinning electron makes a magnetic field. So the only way they tolerate each other is to flip one over so that there's a electro-repulsion, but a magnetic attraction. So what that causes is not that they like each other, they just don't hate each other anymore. So they just tolerate each other, just enough to stay in an orbital together. They don't stick, okay, but they also don't fly apart, right? So the way you accomplish that is one of them's got to flip over, okay? We call one spin up and one is spinning down. So spin up and spin down, okay? So you can put 2 electrons in an orbital as long as they have opposite spins. That's the Pauli exclusion principle, okay? Let's start drawing some stuff up here. Who's the first element on the periodic table? Hydrogen. How many protons does hydrogen have? 1. So if it's a neutral atom, how many electrons does it have? 0. 1. Okay. All right. So we're assuming that we're dealing with all neutral atoms until Friday or one day next week when we start dealing with atoms. But right now, everything's a neutral atom. So the protons and the electrons are equal. Okay. So here's how we draw an orbital diagram for hydrogen. It's so simple, it's confusing. Okay. So we'll have to get a few elements in before this starts to make sense. So hydrogen, we're gonna draw at capital H, that's its symbol, we're gonna put a little dash, we're gonna draw a box. And we're gonna label that box 1s, first energy level, s orbital, and it has one electron in it, and it's spinning up. So we draw that as an up arrow. Okay. Now, what's the next element on the table? Helium. How many electrons does it have? So I'm going to drop them in the atom, right? So 1s can have one spinning up and another one spinning down. So they both go right there. According to the Pauli exclusion principle, that one's full now, right? Okay. So when we go to lithium, it's got how many? 3. So 1, 2. Where's the other one going to go? Oh, we need another orbital. 3. This is 1s. This is 2s. So just like we fill up the bottom of the first row of Connect 4, the next electron's got to go on the second row of Connect 4, right? Okay. Yep.
And you said the 1s and 2s, those are, I know the boxes are the orbitals.
Right.
But the 1s and 2s.
That's the basically called the name of the orbital. It's not really the name. It's the energy level and the type of orbital that this box is representing. Because a box is a lot easier to draw than that S right there, right? So we don't want to draw those shapes all the time. So we're representing each of those shapes by a box. That's simpler to draw, right? I'm even going to simplify it even more in a second. So if you look this up in a textbook or online or somewhere, it's probably going to have boxes, full double-sided arrows, okay? But watch how I do the next one. Because I'm going to get really tired of drawing those boxes in the next week or two. So I'm going to just put a blank, just a dash line, just a blank line. I'm going to call that 1s, 2s. And then I'm going to have a half arrow that points up and a half one that points down, another one that points up and another one that points down. Really, and that's 4 electrons. 2 of them go in the 1s orbital, and the next 2 go in the 2s orbital. Instead of drawing boxes with full arrows, which you are free to do, I'm just going to draw blanks and half arrows because we're going to draw so many hundreds of these in the next few days. Yep.
All right, so let's say, all right, carbon has 6, right?
All right.
So would it become like 3s? So
Almost close, but not quite. You gotta- where it starts to get fun. Okay. So let's do boron first. It's got 5, right? 1, 2, 3, 4. The 5th one's got to go somewhere else, right? So because all the exclusion says that one's full, so we got to go to the next one. So what's the next one? Well, this is where it gets a little complicated. So there we go. So look at your periodic table. All right. First question. How many rows are in that table? How many? How many? Either 7 or 9. I like 9, most people say 9. It's actually 7. Okay, here's, you have to look closely. Number 55, 56, 57, 72. Missing something, right? 55, 56, 57. Here's 58, 59, all the way to 71, and then back to 72. Okay? This goes 87, 88, 89, 104. So we're missing something here. 87, 88, 89, 90, 91, 103, then back to 104. So these two rows are part of row 6 and 7. So there's 7 rows. These are just set out to the side so that the table doesn't look like a big pyramid or something. Okay? All right, so 7 rows. 1, 2, 3, 4, 5, 6, 7. Okay, and there's 18 columns. All right, but if you look, you'll see that the columns are not very uniform, right? It's an odd shaped table. Well, if we break it into some parts, like those 2 columns right there, and we have to do something a little tricky here. We have to think of helium as belonging there. Okay, so for the purposes of what we're talking about here, helium needs to be over there. Okay. Then there is a group of 10 columns right here. There's a group of 6 columns over here. And down here, there are 14. Okay. I see how you can break it up in that those chunks. We call them blocks, by the way. Okay. So there's 4 blocks. How many types of orbitals were there? 4, S, P, D, and F, right? Okay. So there was S, P, D, F orbitals. And how many types of S were there? We chanted it together. 1. How about the P's? 3. And the D's? 5. And the F's? 7. Okay. And Pauli exclusion principle said you could put how many electrons in each orbital? Maximum of 2. 1 times 2 is what? 2. 3 times 2 is what? 6. 5 times 2 is 10. 7 times 2 is 14. Okay. How many columns are in this block? 2. This is called the S block. How many columns are in this block? 6. This is the P block. How many are here? 10. So what do you think it's called? D block. This has, yes, 14, which just makes it the what? F block. Okay. Now, we don't get down to the F block very often. Not a lot of people get down there. A lot of physics, not a lot of chemistry. So, hydrogen had longer arms here. Hydrogen has 1 electron in the 1s orbital. First row, first energy level, first column of the S block. We're pretending that helium is right here for just the purposes of this conversation. Okay, helium has 2 electrons, both of them in the 1s. Okay. After that, we went down to the 2s to get the place for lithium's 3rd electron and beryllium's 4th electron. To get boron's 5th electron, we're still on the 2nd row, but which block are we in? In the P block. Okay. All right, so there are 3 P orbitals, so we put 3 blanks. We put 1 electron right there. So this is the 1s, 2s, 2p. Carbon has 6. Well, the first 2 are in the same place that everybody else's first 2 are in. Okay? And the second 2 are in the same place that everybody else's number 3 and number 4 are in. What do you think its 5th one would be? Same as that one, right? This just keeps repeating itself. The question is, where does the 6th one go? There's 2 guesses that make sense.
Is it down the same line?
either there pointing down or here pointing up, right? This is where Hund's rule comes in. These three orbitals have the same energy. Hund's rule says you got to put one in each before you pair them up. So this electron goes there. 6. We're going to kind of leave off with that right there for today. Now we'll make this point is that little difference, that electron going here instead of here, gives carbon all of its properties, which makes it chemically bond all the ways that it chemically bonds. It's because that electron is here and not here, which makes the basis of all of organic chemistry, which is the basis of all biochemistry, which is the reason that all living things are alive. Okay? It's because that electron goes there and not here. If that electron goes there, there's no life. Everything doesn't exist. So just little things like that make a enormous difference. Yeah.
Okay, so we won't have another one going down until we hit oxygen?
Correct. So nitrogen's going to put one here, and then oxygen puts one here, and fluorine here, and neon there. That's based off of Hund's rule.
So is carbon rule only, do you only use it like, so with the P's, you put all three dashes before you even put the.
The arrows,
before
the
you put
electrons.
arrows.
Yeah.
But with the S block, you put, it seems like you put the arrows before you put the next.
Yeah, because there's only one s orbital, so I don't have choices. It's got to go there. Right? With the P's, I've got, when I add this 6th electron, it's got options, right? They're on the same energy level. So it's not the Connect 4 argument doesn't work. All three of those blanks are on the same level, so which ones are going to go in? It's got to go here before it pairs up. They're going to separate from each other before they partner with each other. Because remember, they only tolerate each other. That spin allows them to tolerate each other. If they can get away from each other, they're going to get away from each other. Kind of like roommates. If I had a suite dorm at the college, right, and had 3 roommates and three bedrooms in the suite, we're going to put one in each bedroom, right? Because we're going to get along a whole lot better that way. But if the college calls and says you're getting a 4th roommate, but they got to bunk with somebody, right? So then we're going to partner them up just because we have to. We're not going to like it very much, but that's what we're going to do.
Okay, so when you get to like D block, whatever, would you put 5 dashes
The 5 blanks.
and then carry it over
One at a time and then come back.
and then come back?
Yep.
And
But
like
y'all are
the,
like 2 days ahead.
and since like D block is like 4th row or whatever, so would you go like 4S?
There's a little trick there. It's 4S, not to get 2 days ahead of myself, but it goes 4S and then it goes 3D. So the D block electrons are 1 energy level behind the row number. Because God said so. That's another fun thing about what we're doing here. So like somebody usually asks, why are the SPD and Fs 1, 3, 5, 7? Why are they odd numbers? Like to come up with that. Nobody came up with that. Okay. That's the way God made the universe to function. Okay. So why are the D electrons 1 energy level behind the row that they fit on the periodic table? Because God said so. Now we're down to that level of physics where it's just like, there really is no why. It just is. So, all right, anyway, we will pick up here tomorrow. What we're going to do tomorrow is we're going to keep going across the roads, okay? The idea is by tomorrow we finish the first 18, okay? By then it sort of starts to sort of make a little bit of sense. And then we're going to throw you a curve, all right? So all this is after we take our little quiz tomorrow. Then we'll throw you a little curve. We're going to come back and write the 4 quantum numbers for an electron, which is different than this. We'll throw that in. And then we'll just keep going, and we won't go past about the 5th row. Once you get to row 6 and 7, things get really weird. Okay, there's a lot of exceptions, things to memorize. Nobody really cares anyway. Most of that stuff is not very common. Mostly rows 1 through 4. We'll dabble into row 5 a little bit. Which means we'll deal with the D block, but we won't see anything really with the F block. But you'll kind of figure out how it works. All right, so press pause right there and we will pick back up with carbon tomorrow.
I don't think you do.
That's not me, right? What's Emma or Drews and it'll keep digging mud?